Swayam Prabha. Digital India. Educated India.
Okay, so welcome back to the session. This is a very exciting session. So we have Bharat Kumar from NVIDIA. He's a senior solution architect there, and he has over 10 years of experience in research and development. He has also written a book on CUDA. So he is the guy to talk about GPU. So over to you.
Thanks. Good morning, everyone. So we are going to talk about a different architecture that you have been seeing so far. And we see that there is a mix of computer scientists and as well as domain scientists. And keeping that into mind, we are going to have an introduction to GPU. And this session will basically cover that. So what we are going to cover here is fundamentals of GPU computing. To give you a perspective, graphics have been used in this industry for quite some time, especially for gamers. You have been using GPUs for playing games. So why does it matter for high performance computing and supercomputing in this time? We are talking about artificial intelligence as well. Why does this architecture is suitable at this time? We are going to look at different ways of GPU programming. This is something, there are some myths around GPU which we would like to clarify. So GPU is an architecture like CPU. It's a different architecture. So we'd like to see how you can program on GPUs, right? There are different approaches. We'll try to cover as many approaches as possible. This will give you a perspective. And there will be hands-on session. There are two kinds of hands-on session. The first one would be happening on AWS cloud. And so we'll be having some sessions with respect to giving theory, but most of it will be practical. So we have already sent you a Slack invite. So most of you, whoever email ID has been given to me, I have sent them a Slack invite, but we'll come to that later on. So let's start with the first session. This particular session will go on for around 30 minutes to 45 minutes, and it's about introduction to GPU computing. So what to expect in this session? We are going to look at very small perspective with respect to parallel programming. And why I am going to cover this, you have been learning parallel programming for quite some time, but it's more evident when you talk about GPUs. To certain extent about evolution on why GPUs are becoming or have become really popular now, and they are become like a general purpose processor. Fundamentals of GPU, which means we are going to differentiate it with the architectures that you have learned so far. We are also going to have a broad overview of the stack of GPU and ways to GPU computing, and it will provide you basically a good starting point. But by the end of the session, after the hands-on, you would be porting a weather code. It's not a simple code, it's code written by Oak Ridge National Laboratory, and it's not so simple. So whatever you learn, you will apply there and make assured that you will be able to go back with a lot of speed up as compared to the original code. The intention is look at a code from a computer science perspective, from a parallel programming perspective, and not from a domain perspective. So that's what we are going to learn in this particular session for one day, which is going to happen. So I think all of you have already done parallel programming. You have been learning it for quite some time now. These 3 days have been dedicated for this. So if I were to just summarize parallel programming, it's a way for a coder, if you have an application or a code, you basically use it for making the performance of your application better. Now, it is a subset of your overall program, obviously. It is a subset of a larger domain which is called as performance engineering. And you use it, what you are basically doing is you are taking a larger problem, dividing into smaller problems which can work independently and try to solve that problem, right? And why you are doing it? To improve the performance, right? But there are different ways in which you can actually dedicate that or chunk it out, right? So there are different kinds of parallel programs which exist. The first one is task level parallelism, which is written there. So you basically break larger operations into smaller tasks, right? So they are called a task level parallelism. The another kind of a problem which we have been and which GPUs are really good about is basically you have multiple data, like you have an image. Just to give an example, graphics, right? What is graphics or gaming? You have an image that you need to paint the pixel on, and you are basically what you're doing is at every pixel of an image of 1024 by 1024, you are deciding which color goes there, red, green or blue. What is it? So you are applying the same ray tracing or whatever algorithm you want to do, but on different pixel data. This kind of a parallelism is basically called as data level parallelism, because you are taking and doing the same operation across different data. So it is a different kind of a parallelism as compared to task level parallelism, which was kind of explained to in Flynn's taxonomy itself. If you would have seen Flynn's taxonomy, the part there is called as SIMD, single instruction, multiple data. That's what GPUs are really good about, right? So let's take a very simplistic example, and why I bring this to you is when you do parallelism, it's not about just applying parallelism, you might have to change your algorithm itself, right? So let's look at this example. There is a professor and he has 3 teaching assistants, and you need to grade 1000 students, right? And basically let's assume it takes, and there are 8 questions in every question paper, and it takes 1 minute to grade every question, right? So total amount of time it will take is around 8000, right? So it takes around 8000. So to maintain fairness, if someone grades a question, like let's assume that, they must grade that question on the all other exams as well, right? So let's look at the sequential version. So we have a professor and we have 4 teaching assistants, and if you see, they are trying to grade, but professor decides that he wants to do everything on his own, and he starts grading them, and he's doing it basically sequentially. If you look at sequential perspective, if he is going to do that, there are total 8000 questions. It will take how much time? Basically 8000 minutes, right? So, and the other TAs are basically not doing anything. Let's say that professor decides this is too much work for me, let me give it to the TAs. But if he decides to do this thing in this fashion, now the restriction is that I can only do it. So if you see, question 1 is done by professor 1, question 2 is done by TA 1, question 3 is done by TA 2, and question 4 is done by TA 4. But if you see, the question paper are in a format that I take question 1 and then pass it on to the TA 1 and then to TA 2 and then to 3, right? Even though all the TAs are working, they are basically not doing anything. In fact, if you look at the time has increased from 8000 to 8000 plus minutes. Why this plus minutes? Because now you need to transfer the pages from one TA to the other. So this is what is called as communication in the world of parallel computing. So as soon as you start making it parallel, you will have this bottleneck of communication as well. But it was not a very fair thing to do, because I don't think so that it's going to help, because the way it has been positioned. Now the restriction here is that all the questions of a particular person get solved one after the other. Let's remove this restriction and let's see now. If you see now, professor is doing 1 to 250 for question 1 and 2. At the same time, TA is working on 251 to 500 student, and he is working on question 3 and 4. You remember we still have that restriction that professor is only doing question 1 and 2. TA 1 is doing only 3 and 4. Still that restriction applies. All of them are doing it. The only thing which is gone now is that there is no, all 3 and 4 is basically getting evaluated for 251 to 500 before even question 1 and 2 has got evaluated. So we have removed that restriction, right? Because we believe that 3 and 4 question are not dependent on 1 and 2. They are independent, right? So let us just do it in parallel. So this kind of gives a flexibility, and now if you see, the time has reduced equally by 4, because we have 4 people who are working in parallel, but there is still plus M. This M will still remain because you are still communicating with each other. Now how much is that M will depend on how much far these TAs are sitting. Suppose this professor is sitting in this building, TA is sitting in another building which is 1 kilometer away from here, it will take more time to communicate. But if the TA is sitting here and the professor is sitting just next room, it will take lesser time. I hope you are getting the picture on where I am coming to, right? Now, let's assume that we still want to stick to the point that question 1 and 2 always get evaluated before 3 and 4. So this is another kind of a parallelism which can be applied, which is called as pipeline parallelism. If you see here, question 1 and 2 is being evaluated by professor, and then after he is done with that, he gives 3 and 4 to the, of the same student, he gives to TA1. And when he is done, he gives it to TA2. So now if you see, you have brought back your previous restriction that 3 and 4 will always happen after 1 and 2. So you are still following that pipeline and you are still following that restriction that you had. And this kind of a parallelism is called as pipeline parallelism, right? So we maintain on the restrictions, but for some time now it has become 2006. Why? Because for certain amount of time there is no activity happening in the beginning, but later on everybody become equally busy in working on something or the other. Now this looks very nice, we have maintained everything, but there is a problem which can occur in real life, right? Let's take this example. Professor suddenly gets a call from the principal and he has to leave in between for a meeting, right? What happens in between? So now everybody else has to now wait till the time he comes back, right? So as you would have seen in this particular example, to solve the same problem, you could have used parallel computing in different ways. You could have used pipeline parallelism. You could have actually changed your algorithm to sacrifice on this dependency of 1, 2 followed by 3, 4. You can change your algorithms. All these things matter when you are doing parallel computing. It is not just about adding pragmas or not just about adding parallel. So you need to think parallel. Now that thinking parallel is something which is very, very domain dependent. Now if you are working in CFD, Jacobi iteration is much more better as compared to the other iteration techniques which exist there, because it is embarrassingly parallel. But in a sequential world, Jacobi is actually not good because it takes more time, right? So these kinds of things needs to be worked out when you are making your codes parallel, right? So now let's switch the gears. This was just a perspective for you to understand why it is important. And when it comes to GPU computing is all about embarrassingly parallel jobs, right? So let's take this example of how things have moved over time. So on the right hand side, what you see is a supercomputer, and this supercomputer was the fastest supercomputer for 3 years in 2002, and you can see the number of racks there, right? The whole building, that floor is actually full of the number of computers, and the amount of performance that it used to give in 2002 is 40 teraflops, right? Now this 40 teraflops today for the fastest supercomputer is equal to one node, one machine, right? So think about a supercomputer which was filling this whole lots of rooms, which is now been replaced by just one box, right? This is how supercomputing has evolved. It has become, supercomputing is not just restricted to, say, a cluster environment or something which is big. You can do this supercomputing now even in a box, right? And this is a power which has been brought ahead with respect to GPUs. If you look at Summit supercomputer, it is basically having 6 GPUs within one node. And that's how it is able to get such a big performance gain that we are talking. If you look at from a different perspective, how things have evolved over time, earlier days you used to have, this is something that you have studied in these days, the way the architectures were built and the way you used to program has also changed. You used to always have a single core machine and then it was attached to a memory where you will allocate and start using it. Now, even whether you ask for it or not, you will never get a single core machine. It's not available anymore. So this is how the earlier architectures were, and the way you used to code also was like, there's like one of the example on how it used there. If you see, this machine was able to give you megaflops, right? And this is how fancy it looks like. Look at the number of wirings it has. But if this machine was running from the time it was envisioned there at that time till now for so many years, it will give you around 200 petaflops. This is equivalent to the Summit supercomputer running in 1 second, right? So if this machine was running from the time it was there till now is equivalent to the Summit supercomputer doing all this calculation in 1 second. So supercomputing has basically evolved. Now this megaflop barrier was crossed over when you moved on to a different architecture. Now this different architecture was a multi-core architecture where you have multiple CPU cores, all of them accessing the same memory. What did it help? It basically helped you to go from megaflop to gigaflop. But what did it change? Now people had to write multi-core programs, right? They had to learn something called as OpenMP. They had to learn something called as multi-thread programming, P-thread programming. So not just the hardware changed, your programming way also changed, right? So this was an example, one of the first examples of multi-core. So this is for its time, it's one of the most advanced system actually, because if you see that person standing there, that person is actually, that computer is inside water. It's actually liquid cooled. This is something which happened in 1985, and this is something which is happening now as well. Since the laws of thermodynamics are coming into the picture, your chips are getting really, really hot. There are better cooling techniques which are being exposed, where it is like liquid cooling is something which is a new thing. It's not a new thing. You can see it was already tested in 1985 by Cray. As you can see, we went from megaflop to 2 gigaflops. We went to mega to giga. Now, to reach from gigaflops to teraflops, there was another change which was brought upon to us, right? So your hardware changed, but along with that, your software also would change. So you have now different memory CPUs connected to each other via high-speed, low-latency network. The network which is very popular nowadays is called as InfiniBand network, which is primarily used in your supercomputing and high-performance computing world, right? But what did it result into? Obviously, it improved the performance, but what did the programmers had to do? They had to learn something new called as MPI programming, because you moved on from a shared memory architecture to a distributed memory architecture, right? So you have been moving in this fashion for a long time, right? So your hardware changes, your software changes, and the programmers have to basically keep on updating their software based on how this evolvement happens. So this is another example from Cray again, which if you see now I've reached teraflop of operations in 1993. You can see the cables earlier were not so thin as you see nowadays, but this was giving around 150 megabytes per second transfer speed. Nowadays you have like connections which are much more better than that. But after that, for quite some time, there was a gap which was seen. And if you look at this study which was done by Stanford, and the name of the study is called as the End of Road for General Purpose Processors and the Future of Computing. Basically what they did was they actually studied a lot of phenomena. One of the phenomena is seen here, which is already known to you, which has been covered, which is called as Moore's Law, right? Which basically states that with every 18 months your number of transistors increases. Transistors increasing is indirectly proportional to your performance of your application increasing. And that's what was kind of observed for a long time. But if you see that single-threaded performance kind of started flattening out, right? There were a lot of innovations which happened during this time because of which everybody was getting good performance. To name a few, like you went from 8-bit, 16-bit, 32-bit to now you are at 64-bit instructions, right? So you can actually allocate 2⁶64 amount of data. So your instruction set basically consists of 64-bit. You had something called as, there was a quiz which was there some time back on branch prediction, right? Branch prediction, like things came into the picture to make sure that you are able to get the instructions prior itself and you don't wait upon, because of branches, you don't lose out on any latency basically, right? There were different kinds of innovations which were brought into the CPU architecture to make this graph keep on going, but finally it was flattening out, was the observation which is seen in this study. It's a very popular study, you can go ahead and read about this study. But what made this graph go up was something which has been evident now. You can see more and more GPU computing which is there in almost all the supercomputers which are coming out. So this is where GPU computing has evolved. It was trying to bridge this gap with respect to the performance. You can see the graph of GPU computing, it has been still giving you more and more performance, at least 50% performance, in many cases more than that performance year on year, right? And that's where GPU computing plays a big role. And it's not just about the performance, and we'll come to that part later on. It's not just about the performance, it's about green computing and it's about other aspects as well. Because the more performance you want to get, the more power you need, the more power you need, the more investment. If you look at the dynamics of purchasing a supercomputer, it's not the purchase which is more important, but to maintain it is more important, because the electricity bill and the cooling bill is much more as compared to buying that supercomputer anymore, right? And it is more evident where there is a convergence which is happening. The largest number of CPU which gets sold out is in which is the largest CPU which gets sold out? Which architecture? Sorry? So, okay, so I just will give you a hint. It's an ARM architecture, right? So ARM architecture. 99% of the CPUs sold in the world are embedded for embedded systems. Exactly. So the market is. So why is it very, very important for you? Because finally this is becoming. Why do we have ARM really popular in this embedded world? Because ARM is very, very power efficient architecture. It was built from the bottom up to be very, very power efficient, right? You will never buy a phone or an embedded device where the battery drowns in like half an hour, right? No matter how much performance it gives you. Now this is something which is very important in the supercomputing industry as well, because as you keep on becoming larger and larger with respect to petaflop, now we are in the age of exaflop. You will see exaflop machines coming very soon. The amount of power it will require is basically very, very important, and it's not just the performance which matters. So it is performance per watt. What is your power, right? Which is the key characteristic and not just performance, right? Which is going to be driving this industry. And GPUs are very, very green. If you look at the green 500 supercomputers, GPUs kind of dominate there as well. What you see on the left hand side is our way of telling that it's not about the hardware, but it's about the software stack as well. So we created an architecture, we changed the operating system, there were new algorithms which were developed, and finally applications started making use of it. Now it has taken us from 2007 till this time to make this software stack available to you, which is the key and not just the hardware. So the platform that we created, which was away from the graphics world. So GPUs were always used for graphics. As I gave you an example, in graphics also what we were primarily doing was parallel programming, right? We are painting pixels in parallel. Is this correct? Right? So it was always made for doing parallel programming, but it was used in a graphics world for gaming and the other purposes, right? But people like us who work in this general purpose computing, doing things like sorting, doing things like convolution, and all these operations could not understand, or it was not very easy for us to understand the graphics pipeline. If you are a graphics guy, you will know that you need to understand textures, you need to understand shaders, you need to understand the whole pipeline of how graphics get sorted out. Now for us, we wanted something which is very, very natural to us on how we write programs. So NVIDIA created something called as CUDA, which stands for Compute Unified Device Architecture. Now we don't use that acronym to that, usually people just call it as CUDA. So we created this architecture which has become the most evident or most used parallel computing architecture at this point of time, which is the parallel programming model. We provide you the GPUs, but what is important is the stack above it as well, right? So we give you different kinds of systems are available, supercomputing system. You can also have it in your laptop. You have it for embedded devices, like NVIDIA is now very, very well known in the space of artificial intelligence. And when you talk about things like autonomous driving cars and all, it is basically driven from our GPU architecture. So we have the same GPU which goes in your embedded devices, it goes into your supercomputing devices, the same goes into the graphics devices as well. We didn't create a different architecture. It's only one architecture across all of these guys, right? So if you code on your laptop, the same can run on the supercomputer, and the same can also run on this embedded device that we are talking about, which is an autonomous driving car. And that is something which which is very, very critical to CUDA system, because you cannot create different programming models or different architectures for different purpose, right? Over that, you basically have your applications, frameworks, libraries, and all those things, which is a whole software stack, and then people use it for different domains. To give you an example, if you are a CFD guy, computational fluid dynamics guy, you will look for a library called as AMGX, which is basically a solver library. If you are a molecular dynamics guy, you will directly start using something called as GROMACS or NAMD, and all those applications are by default GPU accelerated. You will not start writing code there. If you are an artificial intelligence guy, you can name any deep learning framework like TensorFlow, Theane, Torch, or anything you name. All of them make use of a lower level library called as CUDNN, which is already GPU accelerated. You don't need to write any parallel code, right? So this is the whole stack, which is at this point of time, which is called as the CUDA platform, which is available for all the programmers who are using it at this time. Now, when we created this architecture, we said that we are not best of all the world. We cannot create an architecture which works and does everything in your program, right? If you look at why, forget about GPUs, why were network devices made? Can networking not be done by any other, by say CPU? Same thing, the graphics, can it be done by CPU? Yes, it can be done by the CPU. But is it good at doing that? No, right? So the question is that I don't want to be best of all the worlds. I will create an architecture which is good for something called as parallel computing. Now, rest all work is good at being running on the existing architectures, which is CPU. So it's not an alternative. Your program will always have two parts. And if you would have heard about it sometime back during these sessions, have you heard of 80-20 principle? It's a very general principle. It basically states, like there's a lot of study which happens, like 80%, like Microsoft did a study previously, and they found out that 80% of the bugs basically come from 20% of the code. If you look at your codes, 80% of your time will be spent in 20% of your code, right? And primarily, if you will see, they are for loops, right? They're primarily for loops. So why not to just do it? So if you see that for loops basically go into the GPU, and rest all part, which is primarily sequential part of the job, still runs on the CPU. And that's why this kind of a programming is called as heterogeneous programming. The reason behind that is because you now have not just one kind of architecture, you have two kinds of architectures working together with each other. That's why it's called as heterogeneous computing, right? So you have some part running on the CPU, some part running on the GPU. And that 5% of the code, this is just a sample code, obviously that mileage varies based on the code that you're going to do, is the one which runs on GPU. And this, how much speed up you will get, will be defined by Amdahl's law, which we'll cover later on if it is not covered. So it's also called as accelerated computing because you are accelerating your code, right? Heterogeneous computing, accelerated computing, these are all terms which you keep on hearing. But this is kind of a cartoonish figure which kind of represents the reality. Now you might ask, why doesn't GPU work like CPU? There are two different architectures. Now think of it like this cartoon figure is kind of representing the difference in architecture between CPU and GPU. One difference that you will see on the right hand side is that you see a lot of small boxes which are fundamentally cores, right? So GPUs have lot many cores as compared to CPU. Now does that mean that they are the same cores like CPU? No, they are different cores. If you see the CPU cores on the left hand side of your diagram, which is large boxes, these large boxes are basically CPU cores. Nowadays you get up to 40 cores. On GPUs, if you see, I'll show you in a diagram later on as well. Volta architecture is 5120 cores, right? Two different types of cores doesn't mean they do the same thing. So CPU cores are more complicated. GPU cores are more simple, right? That's why you see this difference in this sizes. Other thing that you will see is CPU actually keeps a lot of space for other activities as well, right? It's not just meant for arithmetic and logic unit, which is your course. It does something else as well. So both of these architectures are different. Now let's look at what are its strengths and what are its weaknesses, right? Now CPU is very good at doing something, GPU is very good at doing something. They are not alternative to each other, and they both work together to make your application go faster. One of the biggest CPU strength is that it has a very large memory. What is the maximum amount of memory you can get in a node? Any guesses? 1 TB is the example. What is the theoretical limit? I already gave you the answer some time back. It is 2 raised to 64, right? Because you have 2 raised to 64 bit instruction set, you can point to these many locations, right? So you can have a pretty large memory. Every CPU core runs at a very high frequency, right? Is frequency okay with everyone? So frequency is something, if the frequency is higher, your core is running at a higher speed, right? So your CPU cores actually run at a very higher frequency. Nowadays the CPU cores run at 3 to 4 gigahertz of frequency. So every core is very powerful. It runs at a very high speed, right? And CPUs are very good at latency optimized via large caches, right? So CPUs have a lot of cache. You saw that other part which was there. So CPUs basically will have a lot of caches. Why do you think caches are required? Is it hide the latency or reduce the latency? That's the most important question actually. It reduces or hides the latency? It reduces the latency basically, right? It's like that rather than going very far to a memory which is RAM, if you look at the CPU memory architecture, so your memory architecture looks something like this. This is your CPU. So my handwriting is not that good on this. I'm trying it for the first time. So which is the highest amount of memory? RAM, right? What is above it? Have you heard of L3 cache? Then you have L2 cache, then you have L1 cache, and then registers, exactly. So the higher you go like this, what happens? It is faster or slower? It is faster. The lower you go, what do you get more? The size basically is more, correct? So you keep on going higher and higher, the faster you will get. If your data is always at the higher level, you will always get higher speed. If your data is at the lower level, you will never get the speed that you would expect out of it, right? So to give you an example, we will have that session later on as well. One of the architectures is really good. You can design a particular data structure as structure of array or array of structure, right? So we'll cover that part later on as well. One of them is very good for cache, another is not very good for cache. And this is something which is very, very important, for which if you are using and writing a multi-core program, you need to write a cache-friendly program. Otherwise, it is not so good at getting the performance because most of your time will be spent in memory rather than doing compute. CPUs can run small number of threads very quickly. Suppose it was a 20-core machine CPU, how many threads can optimally run on that core? What is the optimal number that is recommended? 1 thread per core is generally the number. With hyper-threading enabled, they are usually okay with 2 threads per core as well. So it can run those cores very, very fast, those threads very fast on that core. What are the weaknesses of CPU? It has very low memory bandwidth, even though it provides you a very large memory, which we saw here, RAM, which is 2 raised to 64. The memory bandwidth, which is generally referred to as DDR3, DDR4, is not so high. So now your operating system like driver stack and all, they need to know GPUs, right? So when you want to do that, you have to create operating system based modules which gets loaded, and they basically understand the GPU as a hardware resource. And when it tries to understand the GPU as a hardware resource, there are different optimal techniques which can be done. I don't need to go into the optimization part of it, but if you were to say access a memory, you can bypass the CPU completely and you can directly access the GPU directly. It's called a GPU direct technologies. So you can have different kinds of optimization at the lower level so that your operating system understands this new architecture, which is much more performant, and it is a different architecture. So you need to write a different communication protocols and all those things to make it work efficiently. Compilers are completely different. We'll come to that part. Okay, so we came to this part. So it has very low memory bandwidth. So if you look at the latest CPUs, the memory bandwidth that you will get is around 200 gigabytes per second. And the cache misses are very costly. Please mind that if you write a program on CPU alone, and if you don't write a cache-friendly, say, the data structure, your performance can get hit by almost like 10 times or so. So you can get many folds slower within sequential code itself. And CPUs, since they run at a very high frequency, the performance per watt is also very low, right? Because you are actually running at a higher frequency, that means you are consuming more and more power. Now, since I talked about memory bandwidth, you have to understand one part of it. If I were to show you a very simple example, suppose I was doing this operation, A equal to, maybe this is better, right? A of I equal to B of I plus C of I. So this is a very simple operation, correct? And I can do this in parallel. Can anybody tell me how many memory operations I am doing and how many arithmetic operation I am doing? 3 memory operations, which is 2 reads and 1 write and 1. So if I give you more and more compute, will it help? Or if I give you a faster memory, will it help you? Faster memory. So these flops and this number of cores and all those things don't matter in case you are memory bound. So there are different kinds of applications which exist. Like there are memory bound applications, there are compute bound applications, there are latency bound applications. Communication bound, which falls in the range of latency as well. So based on your application, this is what will also define your performance. I wanted to bring it out because I said that it has very low memory bandwidth, right? So what about GPUs now? Now first thing about GPUs that you will see, GPU has a very high memory bandwidth, right? So GPU's memory bandwidth, if you see the latest one, has 900 gigabytes per second, right? It gives you much more higher memory bandwidth. It has more number of compute as well. As you can see the number of compute which is there, Volta has 5120 cores. It is a latency hiding architecture. It is not a latency reducing architecture. So what do I mean by that is basically coming back to the previous diagram that we saw. So your CPU architecture was like this. So you had your RAM, L3, L2, L1 and then R, resistors, right? Now GPU memory architecture is not exactly like this, but it is kind of inverted. Okay, so you have a lot of resistors, then you have cache and you have RAM. So as an architecture in GPUs, we made a decision that we are going to have lots and lots of resistors, right? Now resistors are very costly, but they improve your performance like anything. The reason why I am trying to tell you this is, going to the fundamentals that you learned some time back, I think there was a quiz question as well on what a program counter is, right? Now let's take a very simplified view of a program. What is a thread? Thread is a execution unit, but is it a hardware concept or a software concept? It's a software concept. So suppose you were writing a thread program in your operating system. How will you define it? Maybe a structure, right? Structure. And then inside that structure, what will you have? Stack, heap, program counter, right? Now every thread maintains this structure. Where will it maintain this structure? It needs to allocate that memory, right? Where will it allocate? It tries to allocate it as high as possible in your hierarchy. If it can fit in registers, good. If it cannot fit in register, L1. If it doesn't fit in L1, it goes to L2. If not in L2, then L3. Right? That's how it works. Right? Have you heard this term called as context switching? Right? Context switching is, if I had 2 cores and if I launch 4 threads, right? If one thread is waiting for something, so think of it like there are 2 chairs and there are 4 people, only 2 can sit at one time. And if one person is waiting for something, he can give his chair to someone else, right? So if 2 threads are running, and if one thread is waiting for something, it can give thread 1 can give its seat to thread 3 for executing. This is called as context switching. Now, the more number of threads I launch in a CPU, where will this data structure go? Earlier it is at a higher level, it will keep on dropping down, right? And every time it drops down, the more time it takes for me to get up from this chair and move out, right? Because I need to take my luggage, which is my data structure, put it somewhere else, take this guy's luggage and again put it back. So now this context switching in case of CPU is very costly affair because there are very less number of registers available. In case of GPUs, there are so many registers. Everybody gets a huge amount of registers. So if one thread is waiting for something, I will just switch from one thread to the other without any loss of efficiency. And that's why on GPUs, you actually launch thousands of threads. You cannot launch hundreds of threads. GPU is a massively parallel architecture. So you have to launch many threads. In fact, you have to launch more number of threads than the number of cores available. If you don't have so many amount of parallelism, GPU may not be the right architecture for you. I can't use it for just sorting 100 elements. It's not meant for that. It's like killing a fly with a cannon, right? You will not kill a fly with a cannon, right? You will use some other thing for doing that. So GPU is a very massively parallel architecture. And if one thread is waiting for something, it will actually jump to the other thread without wasting any time. So in GPUs, you can actually launch many number of threads because as an architecture, we made this decision that we will have more and more registers so that when one thread switches to the other, it will not take a lot of time. This is a very key difference between CPU and GPU. So if you are making use of GPUs, you should have that kind of a parallelism available to you, right? So it gives you high throughput and it is high performance per watt. Now this is very important. CPU cores run at a very high frequency of around 3 to 4 gigahertz at this time. GPU cores are not that fast. GPU cores run at a 1 gigahertz frequency maximum. So every core is 3 to 4 times slower as compared to a CPU core. So if you run a sequential job on the GPU, it is going to be minimum 4 times slower. Understood? It's going to be minimum 4 times slower. But you have a lot of them. That's why GPUs are more green. Because they run at a lower frequency, so you consume lesser power and you get more flops. What is the weakness of GPU? Obviously, GPU is not the best for doing everything. So you get lower memory capacity. I am giving you 900 gigabytes. So that's why I cannot give you 1 terabyte of memory because it's not possible with the technology currently available. The maximum memory that you get in one GPU at this point of time is 32 GB. So if you have 2 GPUs, it becomes 64 GB. So that's how the GPU memory is. So if it fits within that GPU memory space, it is going to be very performant. And every thread performance is very small. So this is an example of the latest GPU which exists at this time. You can see it has 21 billion transistors. The number of cores which are available are 5120 cores. It gives you really good performance. And as you can see, the speed is pretty high, right? So this is just a sample example of it. If I were to summarize the difference between CPU and GPU in a very simple terms, if I were to go from here to say Lucknow airport, alone, I will prefer maybe a bike or something, because bike is faster, right? And it doesn't get stuck in traffic and stuff like that, right? But if I were to take all of you with me together to the airport, what will I choose? Maybe a bus. Bus is slower as compared to a bike, but it can take all of you together with me. So you see the difference? So bus, this is the fundamental difference between CPU and GPU architecture. GPU is basically a throughput based architecture, and if you see CPU is basically a very latency optimized architecture. So GPUs and CPUs work together because your code will always have some part which is fundamentally not parallel in nature. It's not possible, there is no application in this world which is 100% from the start till the end always parallel, right? There is no application like that. So the part which is sequential runs very, very optimally on the CPU. Some part which needs to run in parallel on the GPU goes to the GPU. Both of them work together, right? And that's what is the key message in this difference between architectures. Now, GPU is a architecture, ARM is a architecture, x86 is a architecture. What is the first thing that you do when you want to write an application? Choose a programming language, right? Should I choose Python? Should I choose C? Should I choose Fortran? What should I choose, right? So similarly, GPU is an architecture, and you can program it using different languages. You can program using different approaches. Every approach is different from each other, right? The first approach is called as library approach. Then we have directive-based approach and programming language-based approach. We'll try to cover them as much as possible during these sessions. So let's look at them. So the first one is libraries. So by the way, so there are already, first thing is applications themselves if you ask. If you are in AI world, you will never write a parallel program mostly, because already all the frameworks have been GPU accelerated, already. They already have been, somebody has already done the work of writing parallel convolutions, right? Somebody has already done the work of writing those parallel algorithms. So the best parallel program is something that you don't write, right? It is something which some expert ninja programmer has already written. Nobody writes matrix multiplication anymore in parallel. It's just for learning purpose. If you're working in domain, you will actually start using libraries like CU, BLAS and all directly. Don't start writing parallel programs. If you're in molecular dynamics, if you're using GROMACS, just use GROMACS. Don't write something which is again parallel in nature, because there's a parallel version of GROMACS already available. So there are so many applications which are already GPU accelerated. The first thing is to go ahead and use them. If you are looking at something more modular, you can make use of different libraries which are present. There are different kinds of libraries, parallel algorithm libraries. If you are in graph, you can use NVGraph. If you are in a linear algebra space, you have BLAS routines. If you are using CUFFT, you have FFT routines. In the signal or image space, you have deep learning libraries. All these libraries are kind of present. There are so many set of libraries. You can go ahead and just go to this website which is mentioned there and just start using it for image processing and all. Don't start writing codes which are already present in the library. But you have another approach. In case there is no application, you are creating your own application, there is no library present there, then you have to write your own parallel code. You have been learning this parallel codes for quite some time in this lectures which has happened. You have written OpenMP code as well. You have written MPI codes. We are going to look at another programming approach which is called as OpenACC. OpenACC, ACC stands for accelerator, which is very similar to OpenMP, but it became really popular when heterogeneous computing became really popular. And the fundamental reason why this programming model was born was because of this approach, that you have two kinds of architectures, CPU and a GPU, which is more dominant, and use it in your programming. We'll cover this in more detail. It's a very, I would say, the scope of this is increasing day by day. Let's take an example. If your algorithm that you were porting was this, which is z equal to alpha x plus y. X and y are vectors, alpha is a z, x and y are vectors, alpha is a scalar value. If you are going to implement this in parallel on a GPU, you have different ways in which you could do that. The first one is something called a directive based approach, which is OpenACC. We'll be covering this in more detail, but as you can see here, this is your sequential program where you are doing this operation, and just before that, like your OpenMP, you are putting a pragma, hash pragma ACC kernel, and it basically creates a GPU CUDA code behind the scenes for you, and you don't need to understand the GPU architecture, right? This is the easiest approach which people have been using. This is another approach, same thing in Fortran. So here you have exclamation dollar, right? This is the first way. Second way, if you knew there is a library for doing that operation, you could have just replaced it with a call. There is a library called as CUBLAS. CUBLAS is a library which does this operation, and I can just replace that call with a BLAS routine here. And I could have done the same work on the GPU, which have been really faster. Or suppose I wanted to get the best performance, if I wanted to learn CUDA architecture and get the best performance, I could have actually written my own CUDA C code. As you can see, this is a sequential code, this is a parallel C code. It's not that you are learning a new language, right? You're not learning a new language, you are just adding some additional keywords. As you can see, you're launching a function which is called as saxp here, which is a GPU function. How do I know it's a GPU function? It's appended by a keyword called as __ global, and the number of threads that I'm launching is how much? 4096 into 256. That many threads I am launching in one shot on the GPU, and that much data will happen in parallel on the GPU. This operation will happen in parallel on the GPU. So I could have chosen this approach, or I could have chosen a C++ based approach where I could have used a particular framework called as Thrust, which is equivalent to C++ STL. It's a parallel STL version, and if you can see, I am doing the same operation here in more of a C++ way by using syntax or by using an API called as transform. It does the same thing. You can see these are iterators, and then you are doing this operation of multiplying alpha 2 to a first iterator plus the second iterator. Same thing could have been done in C++. If you are a Fortran programmer, you could have used a CUDA Fortran way. Same thing that I told you, like C++, I am declaring it as global. I am launching so many threads. Same thing happening in Fortran. If you are a Python guy, you could use something called a Numba. Numba is a module which actually you can just import. You can see you are doing an import of vectorized function, and then you are saying that I want to run this, my target is CUDA, and I am doing the same operation here. Again, same thing in Python. Or if you are an enthusiast, if you are a compiler guy, and if you are in computer science, you can develop your own DSL, domain specific language, and still target CUDA because we have made the front end open, right? So there are so many flexibility which has been given to you. So the first choice for a user is always to choose whether he wants to go with the library based approach, which is the first choice obviously. He wants to be portable across using directive based programming. I don't want to spend a lot of time. I don't want to understand the architecture. I can go OpenACC or directive based, or if I want to get the best performance, I can choose CUDA C, CUDA Fortran, or I can choose those lower level constructs as well, where I define which thread accesses what data and in what manner. So as a programmer, it's the choice that you have with respect to GPUs. If you are in a deep learning world, especially, the whole stack is kind of already there. Mostly you will never write any parallel program, because if you see all the libraries are there. CUDNN is a deep neural network library which does convolution operations and all. We have BLAS routines already there. TensorRT is a library for deployment. Sparse library is there. So we have a video analytics library called a DeepStream. All those libraries are kind of present. And if you want to contribute back to the community as well, this is all open source. So you can actually go to GitHub. This is called as Rapids. You can go and download the library, you can contribute back as well. So it has all these components which are mentioned here. Everything works still on CUDA. In fact, if you see the AI revolution, NVIDIA was not the one who identified that graphics processors, GPUs, are very good for artificial intelligence. There was a researcher who made use of GPUs for bringing back deep neural networks in this AI space. And the reason why it became possible was because he was able to run neural network within his time frame that was good. If you would not use graphics processor, it would have taken him days to weeks to months to even do one kind of a training. He made use of GPUs, he made use of CUDA. He wrote these frameworks were not available at that time. He wrote his own code, which is all these approaches, and he was able to get this thing. And from that time, GPUs has become the platform for making use of artificial intelligence, right? So we expose this platform called as CUDA, which is for you to develop different approaches. Now you are the one who will choose different approaches on that. Another thing which is also changing, which NVIDIA is also trying to push a lot, is something called as containers. Now, how many of you write papers or plan to write papers? Research papers? Almost all of you. Have you tried to read somebody else's paper and tried to reproduce it? How many of you were successful in the first attempt? If I would be really surprised, because the author would have been really nice. Because if you see, when somebody does research, there is a lot of dependencies which exist. This OpenMPI version, this particular library version, this kind of a dependency, that kind of a dependency. And when I ran on this architecture, it gave me this output. When I run it on the other architecture, it just starts giving me different output. It's pretty common, right? Now this is something which is getting solved by something called as containers. Containers are like a very simplified version of virtualization, where you are not running a virtual environment, but you encompass all these dependencies into a very packed thing. So instead of doing installation of OpenMPI this version with Blast this version and this version and that version, you can just say Docker pull, and it will actually pull all the dependencies on your machine, which you can just start running on, right? So it is kind of simplifying this space. It is very much evident in the AI space, and it is becoming really popular in high performance computing and supercomputing as well, where if you are writing something, if you want it to reproduce it, you can just create a container out of it, so that I don't have to think of it like this. If I am moving from one machine to the other, again I have to do that installation. You don't have to do this with Dockers. Containers, Singularity and Docker are the two famous container environment. So you can just create a Docker and you can just pull it onto another machine and just start using it. You don't have to do those installations again and again. So NVIDIA has taken this initiative in terms of pushing containers. We have something called as NVIDIA GPU Cloud. The name is Cloud, but it basically means that we have a repository. It's like an app store. It's like an app store for your applications. Like your Android has App Store, Apple has Apple Store for application. In your mobile space, think of it like this. If I didn't give you Play Store and I told you, oh, you first download the code, compile it, and then create your application in your mobile, would you use it so efficiently? No, right? Same thing we are trying to do in this high performance computing world, that you just pull the container and start using it without getting into this bottleneck of installing stuff. Right? So we have created that app store, which is called as NGC, and it provides you so many basically improvements, right? You don't have to waste your time, maintenance becomes easier, productivity increases, your installation time decreases. So you can actually go, in fact, the hands-on session which we are going to do in Amazon is going to be based on these Docker containers, which will be deployed onto Amazon in the next session, right? So this is something. If I would say to summarize, first thing is, it's a full stack optimization. It's not just about the hardware. You need to look at the whole software stack. There are multiple choices of programming on GPU. You have to choose which is the right approach for you. And one is not an alternative to the other. What I mean to say is you can actually combine OpenACC and CUDA-C together. right? You can start with OpenACC and take one kernel which is very, very important and just make that as CUDA-C and make it much more optimized. They coexist with each other. CPU and GPU don't compete with each other, they complement each other. And so universal hardware stack, I have already covered that part. And this, I hope that this gives you a good introduction to what is the fundamental difference between CPU and GPU, why GPUs are becoming really, really popular now or become the standard at this point of time in this supercomputing and high performance computing world, and why they exist and how to use it. After this session, the next section is all going to be hands-on with respect to how to write parallel programs on the GPU. So if you have any questions, I am free to take those questions. This one you are saying? Yeah. So now this depends. So it's not just you get a big resistor cache. So we have a core which is a bigger core which is called a symmetric multiprocessor inside our GPU architecture. Maybe in the next version I will show you more version of it. And resistor is divided among them. And then within that SM, which is called a symmetric or multiprocessor, sometimes people also call it a streaming multiprocessor, you have more cores. So it's divided among them as well. So based on the number of threads that you launch, you will get the number of resistors. So like the maximum number of resistors in Volta is 255 resistors per thread. So if you launch lesser number of resistors, threads, you will get more, right? So that way you will keep on getting divided. What will become slow? No, that's the quality of resistors, right? So resistors, as many you have, everybody gets its own chunk and it will not be, it's the lowest latency layer above everything. It's the fastest.
It was told that if you have large amount of SRAM or cache, then the access to that cache or SRAM becomes slower if it's too big. That's why they give it small. That was something related to microelectronics. I think she's referring to that. So that is. But anyway, in this case, what we are saying is that amongst those that are present, this register file will be the fastest because it is closest to the CPU. That statement is still valid.
Yes.
So what that professor was referring to, yeah, you cannot make it something like
yes. So that based on the processor electronics, we keep on changing. So if you look at our architecture, in Kepler was our first version, there were lesser number of resistors. As the technology keeps on changing, we keep on adding more resistors, but there will be a limit to that as well. Numba or? How should I answer that question? So this debate has been there for quite some time now. So C versus Python itself is a big debate if I were to put it in that fashion. I would say that if your application is having enough time to spend on a GPU, where the time is spent is in the beginning when you launch it, correct? It's an interpreted language, right? So in the beginning is when the initial time is spent. After that, if you are spending a lot of time on the GPU, it will be equal to your CUDA-C, right? But if your every launch is very small, say few microseconds or few milliseconds, then that cycle will be more bottleneck as compared to a CUDA-C, right? So it depends on your kernel that you are launching. What is the content inside it will define how much is the difference in performance. But if I were to give a general answer, CUDA-C will be always faster.
Can you also briefly explain HBM memory?
So HBM memory is a new memory that we came out with. It's basically a 3D stacked memory. So earlier your memory was not 3D stacked. So HBM2 is a new technology in this memory space where you can actually 3D stack the memory, which reduces your latency and it can increase your bandwidth. your general memory that you see, which is DDR3, DDR4 and all that you see in CPU is not 3D stacked memory. It's a different technology, like DDR is the name, right? So HBM2 is a 3D stacked memory which provides you, it's like, I don't have the diagram right now, but you are stacking one over the other, and think of it like you have just put a hole where they can talk to each other via that. So it gives you more bandwidth and at the lesser latency. It's just the name of the technology for getting faster bandwidth. Yeah, so Volta is HBM2. It's all, that's why it gives you 900 gigabytes per second, otherwise it is not possible to get that.
So generally, we measure the efficiency of serial algorithms in terms of space complexity and time complexity, or when or when like that. How to measure efficiency of parallel algorithms?
Okay, so that's a very good question. Let me ask and twist the question and bring it back to you. So the question is basically, generally you measure the performance in terms of time complexity and the space complexity and all of an algorithm, right? How do you measure it in a parallel computing world, right? So let me ask the reverse question actually. Okay, it's a very methodical interview question. Which is the best sorting algorithm? Anybody can answer, by the way. Okay, so what kinds of applications? Let's talk it from a perspective of time complexity. Which has the best time complexity? Quicksort, what is the time complexity? Best time complexity. N log n? What about heap sort, merge sort? That's what you are hinting to based on the application? Okay. Now let me ask you a question. Which is the best sorting algorithm on GPU? Radix sort? Why radix sort? Sorry? Exact. So the best sorting algorithm is what suits your architecture. One of the example which was given here is radix sort, or there is another kind of a sort called a bitonic sort, which are very, very popular in the GPU world. Because if you see, they're actually working at bit level, and they're kind of, it's very easy to make it parallel. So you will actually be defining it in those terms when you're running it on a GPU. So you will primarily use radix sort or maybe a bitonic sort in that particular case to run on a GPU architecture. If you're running a sequential algorithm, and then based on the data, you can choose the different kinds of sorting, merge sort or say heap sort or another kind of sorts. So it just doesn't get restricted to your n log n or your space complexity there, right? So there is no one answer there, but on GPUs, as it was said, radix sort is pretty popular because the way the algorithm it is, it can be easily made parallel, and it follows that pattern of SIMD, right? So it's much more better to use radix on a GPU.
So to measure the performance of a GPU or a CPU, we use floating point operations per second. So which floating point operation is it? Is it addition? Is it multiplication? So I'm not clear about how it is measured. And now in an era wherein floating point operations itself is coming to an end, so they are talking of using posit operations and all those new kinds of number representation formats. So how would it be? How would it go further in terms of measuring the performance of a processing unit?
Right. So that is again not just related to GPU, but in general a general topic in the architecture world. So flops, floating point operations per second. Now, if you look at any architecture, like I don't have the diagram right now, I could have actually put that as backup. But if you see the GPU architecture, you will see cores which are called as 64-bit cores. You will see a core called as 32-bit cores. You will see integer cores. You will see a core called as tensor core. The tensor core is supposed to do 16-bit multiplication and accumulate in 32-bit registers, right? So these are different kinds of floating point operations which can happen. Along with that, you have special kinds of units which are doing things like sine, cosine, and all those things. So the numbers that are generally published, because you need to tell something, right? So everybody will publish things like FP64 means it's a 64-bit calculation, right? It may be any. Mostly it refers to floating point calculations like division, multiplication. How do you measure it is basically just you have that formula of frequency multiplied by the number of instructions that you can execute, multiplied by the number of cores, right? That's how it gives that number which is theoretical. Every architecture guy, every vendor will actually give you that number because it is theoretical. You never get theoretical limit. It's not possible to get that. How do you measure it? The measurement in high performance computing is generally done by this benchmark, which also defines the top 500 supercomputer, which is called as HPL. HPL is the benchmark, or it was earlier called as LINPACK. That's how all your tenders also come out, which says that I need peak of this and I need sustained performance of this. Now what HPL basically does is matrix operations. So it basically does matrix multiplication and all. So that's how it is measured, and that's how the top 500 listing also happens. So when somebody is running and saying I want this much of performance, they say I want this much sustained HPL performance of this. Now this is also being criticized at this point of time because matrix operation does not represent the whole kind of a workload. Now people are moving towards application based benchmarks, which means like top 500 list itself has a new kind of a benchmark which is called as HPCG, which is conjugate gradient, which is very popular in CFD or weather world. So you can actually run that benchmark and say this supercomputer actually performs these many calculations for CFD or weather. So this is how it is going actually, is what my take there would be. It is going to be application specific. There will be benchmarks which will come out for molecular dynamics, for CFD, for AI and stuff like that. Like for AI, it has already happened. There is a benchmark which is called as MLPerf. That's the one which is used to define. It has different kinds of benchmarks for different levels, right? It has high workload, lower workload, for deployment, for embedded. It has different kinds of segments. For vision, there is a different benchmark. For natural language processing, there is a different benchmark and all. And everybody has to submit what are the results you get on these benchmarks. So this is the way forward, where, as I said in the beginning, flops does not mean anything, right? Memory bandwidth might be more important for you. It's not just the flops. If you are a CFD guy, you will ask for memory bandwidth. You will not ask for the flops, right? If you are a molecular dynamics guy, you will ask maybe for different operations, right? So that's what is the future. And it's not these kinds of small things. It's application domain specific benchmarks, and that's what everybody has to prove. I hope I answered your question in a different way. Just to add to it, if you look at the new tenders which are coming out, they are saying, if you look at Titan to Summit, when they went from Titan Supercomputer Summit, which is the fastest supercomputing in the world, the tender didn't say these many petaflops. It was one part of it, but it said GROMAX should give me 10 times more performance as compared to my current supercomputer. That's what is my benchmark. It's not flops.